Hey everyone, so you think you've got a solid handle on network planning? Well, I'm here to tell you that the game has completely changed. We're going to dive into how this explosion in AI is totally rewriting the rulebook and, yeah, breaking the very mental model you've probably relied on for years.
For decades, our whole understanding of how networks behave has been built on a handful of pretty solid assumptions. Your brain, your gut feeling, it has a map for how all this stuff works. But here's the thing, that map is now dangerously out of date. There's a new force at play, and it's challenging everything we thought we knew about traffic, capacity, and what causes things to fail. And this brings us to the central puzzle we're going to solve today. It's a real head-scratcher, right? You're looking at your dashboards, you see plenty of capacity, everything looks green, and yet things are breaking. So why on earth is your network buckling under the strain of AI, even when it looks like you have more than enough bandwidth to go around? To really get why things are falling apart now, we've got to take a step back and look at the world that shaped our intuition in the first place, a world that was built on predictable, pretty manageable network traffic. Think about the old way of doing things, like a city's daily commute. It's episodic, right? It gets busy in the morning, busy again in the evening, and it's pretty quiet overnight. It's all driven by humans, people logging in, shooting off emails, grabbing files. It's all based on a simple client-server model, which made it relatively easy to see the patterns and plan for them. And that predictability created what we can call legacy intuition. It meant we could just look at historical averages, pinpoint the peak hours, and then confidently build out our capacity. And for years, this model worked. It worked beautifully. It was the absolute foundation of network design. But then AI arrived. And it didn't just add a little more traffic to the pile, it introduced a completely new physics of how data moves. And just look at how stark this contrast is. Over on the left, you've got those gentle, predictable waves of human traffic we just talked about. But on the right, that's the new AI reality. It's this chaotic storm of communication that's continuous, incredibly bursty, and highly synchronized. We're not just talking about spikes anymore. We're talking about perfectly timed tidal waves of data hitting all at once.
So yeah, that old highway metaphor, it's officially dead. AI traffic is much more like a dynamic, complex fabric. You see, modern AI training uses thousands of specialized chips, these accelerators like GPUs or TPUs, and they're all working in parallel. And they're not just sending data out, they are in a constant, complex conversation with each other.
Okay, let's break that down. You have thousands of these powerful processors all number crunching at the exact same time. Now, to make sure the AI model learns as one cohesive unit, they have to constantly sync up, exchanging these enormous updates. This creates a massive surge in what we call east-west traffic. That's the data zipping between servers inside the data center. It's a completely different animal than the traditional north-south traffic we're used to, which mostly just goes out to users.
So, what happens when this new AI reality smashes head-on into a network that was built on all those old assumptions? Well, that's when we find the breaking point.
This right here, this is the absolute heart of the issue. If you take away only one thing from this, make it this. Networks fail at the edges and the peaks, not in the cores and the averages. Those 5-minute average utilization charts you've been looking at, they're basically lying to you. They completely hide the brutal, split-second peaks where the failures actually happen. An AI workload can saturate a link in microseconds, way before your monitoring tools even notice a blip.
Which means that comfortable old phrase, "we have enough bandwidth," has become dangerously misleading. It's like saying a bucket is big enough to handle a fire hose just because, on average, it isn't overflowing. The sheer, violent intensity of these AI bursts makes average capacity almost totally irrelevant.
And we're seeing this play out in some very real, very painful ways. Those quick inference bursts are slamming VPNs, choking off access for your remote users. Wi-Fi networks are just collapsing under the weight of always-on AI copilots on every single device, all fighting for the same airtime. And the flood of AI-driven API calls, the way apps talk to each other, is causing these latency chain reactions at security choke points like firewalls.
And in the world of distributed AI training, it gets even worse. Because everything has to be synchronized, the entire multi-million-dollar system has to wait for its slowest part. A tiny bit of congestion or a little latency hitting just one node, the straggler, can bring the whole training job to a grinding halt. It magnifies a tiny network hiccup into a massive and very expensive delay.
Okay, so that sounds pretty bleak, I know.
But it's not hopeless. It just means we need a new playbook. We need a new way of thinking about network design, one that puts resilience first and foremost in this new reality.
And this new playbook is really built on 3 core strategies. First, we have to master congestion control. Second, we need to optimize our network topology. And third, and this is the big one, we have to fundamentally shift from designing simple pipes to engineering a true network fabric. Let's touch on each one.
All right, first up, we have got to stop just throwing more bandwidth at the problem and start actively managing the traffic. This means using modern congestion control. Things like RSC-v2 with ECN. All you need to know is that these protocols let the network signal, hey, I'm getting full before it starts dropping packets. And that's the key to keeping data flowing smoothly without those crippling stalls.
Next, the actual layout of your network, both physical and logical, matters more now than ever before. Every single hop a packet has to take from one switch to another adds a little bit of latency. By designing flatter, more direct network layouts, you slash that hop count, and that is absolutely critical for boosting the speed and reliability that these time-sensitive AI workloads demand.
And finally, we have the biggest mindset shift of all. We have to stop thinking about our network as just a collection of individual pipes, each with a certain capacity. Instead, we need to design it as an integrated, scalable fabric. A real fabric gives you multiple paths, it gives you predictable performance, and it has the built-in resilience to handle that chaotic, many-to-many communication that defines AI. So I'll leave you with one final and I think critical question to think about. Take a hard look at your own environment. Is it built on that old model of simple linear pipes? Or have you started building a truly resilient interconnected fabric that's actually ready for the AI-driven future? Because the answer to that question is going to determine whether your network becomes a bottleneck or a powerful accelerator.